0, so there's no acceleration in the direction of movement. When theta is 90 degrees, sine of theta is 1, so the acceleration is the same as it would be for free fall. Alright, that checks out. And because x is L times theta, that means the second derivative of theta is negative g over L times sine of theta. To be a little more realistic, let's add in a term to account for the air resistance, which maybe we model as being proportional to the velocity. We'll write this as negative mu times theta dot, where mu is some constant that encapsulates all of the air resistance and friction and such that determines how quickly the pendulum loses energy. Now this, my friends, is a particularly juicy differential equation. It's not easy to solve, but it's not so hard that we can't reasonably get some meaningful understanding out of it. At first glance, you might think that the sine function you see here relates to the sine wave pattern for the pendulum. Ironically, though, what you will eventually find is that the opposite is true. The presence of the sine in this equation is precisely why real pendulums don't oscillate with a sine wave pattern. If that sounds odd, consider the fact that here, the sine function is taking things